If you look at the Gulf Coast of Texas, you'll notice something curious. There are almost no mountains here. For hundreds of miles, the landscape's nothing but flat plains, wetlands, and low-lying shoreline. So one company decided to fix that by building a mountain. No, of course they're not planning some sky-high New Everest. Their idea is much stranger. They want to put a nearly 1,300-foot-tall mountain underground. Why? Well, that's where things get even weirder. The plan is to send water up this mountain working against gravity. It would literally flow from the bottom to the top. At this point, the whole project starts to sound like science fiction, but it's real, and it's been carefully engineered. So today, we're going to figure out what's actually going on here. So we've got Texas, where engineers are, for some reason, pumping enormous amounts of water deep underground right along the coast. What's the first thing that comes to mind? Drought relief, obviously. The southern states practically melting under extreme heat. Summers here regularly break temperature records. Surface reservoirs dry up almost completely, and local farmers are ready to pray over every stray cloud that drifts across the sky. With this in mind, the idea of hiding freshwater reserves underground sounds like a real salvation. The blazing Texas sun simply can't reach them there. There's no evaporation at all, and clean water can safely wait for the moment it's needed to save cities during the next drought emergency. And to be fair, underground freshwater storage is a real, tried and tested practice used around the world. It sounds logical, noble, environmentally friendly, and most importantly, very easy for all of us to understand. After all, why else would anyone pump water underground on such a massive scale, right? But this is where the whole beautiful picture suddenly falls apart. That theory about saving the state from thirst instantly shatters into pieces. Because here's the shocking part, the water inside this system is absolutely not safe to drink. Not under any circumstances. You can't give it to livestock either. And if you tried to irrigate a farm field with it, you'd kill the entire crop almost instantly and turn the soil into a dead, scorched wasteland for years to come. Because what's going to be circulating deep underground isn't clean spring water at all. The foundation of this entire Texas project is an extremely heavy, ultra-concentrated brine. To give you a sense of how insane this is, this liquid's about 7 to 8 times saltier than the saltiest water in the open ocean. It's a nightmare for anything living. The solution is so overloaded with salt that its properties change dramatically. It becomes extremely dense, incredibly heavy, and highly aggressive. A pretty strange project, isn't it? But what's even more surprising is the equipment they're preparing for it. When you look through the procurement list for a major water-related industrial project, you expect to see the usual things. Miles of standard piping, powerful pumps, filters, maybe tanks for chemical reagents. And all of that's there. But then, buried among the expected equipment, the engineers also ordered massive industrial water turbines. And we're not talking about some compact generator for a backyard stream or a country house. According to the official documents, these are multi-ton steel monsters. Giants like these are the kind of machines you'd expect to find inside a full-scale hydroelectric power plant, holding back the pressure of enormous reservoirs all on their own. And this is where anyone who remembers even the most basic school physics starts to feel their brain melt. Let's quickly remind ourselves how a classic hydroelectric dam works. To generate electricity, you'd normally need a fast-flowing river, a massive dam, and a significant drop in elevation. Water has to drop from a great height, rush downward, and slam into the turbine blades with tremendous force. Only then do the blades spin fast enough to produce power. Now move that whole idea to the actual Texas coast. Around you is a perfectly flat landscape stretching all the way to the horizon. There are no canyons, cliffs, hills, or raging rivers with waterfalls here. If you simply bury an expensive turbine underground on a flat piece of land and connect it to pipes full of heavy brine, nothing magical is going to happen. Water won't spin those massive metal blades just because you want it to. To move a machine like that, the flow needs enormous acceleration. It needs powerful kinetic energy, the kind you only get from water falling from a big height. But nobody's planning to build a skyscraper-sized tower on the surface just to dump salt water from the top of it. That would be construction madness. So we have a paradox. Giant hydro turbines are being prepared for installation, but on this flat coastal plain, there's nowhere for the water to fall from, which can only mean one thing. The engineers are planning to break the rules of nature in the most aggressive way possible. They're going to create a huge elevation drop in a place where nobody will ever see it. Deep underground, there has to be a massive empty space, a real vertical drop, hundreds of feet tall, where millions of gallons of brine can fall. And that's where we run straight into the brutal reality of Texas geology. Something builders sometimes describe as a real nightmare. Just imagine the scale of the task. You need to create a completely empty underground void roughly the size of a large American skyscraper. What seems like the most obvious solution? Looks simple. Bring in heavy equipment, hire an army of workers, and start digging down. But along the Gulf Coast, that trick doesn't work. The ground here isn't solid, reliable granite. There's very little hard bedrock where you could simply carve out a solid underground bunker meant to last for centuries. The geology of Texas and neighboring Louisiana is more like a gigantic layer cake made of soft, shifting sedimentary material. Millions of tons of sand, wet clay, unstable silt, and loose gravel. Try digging a deep hole on a sandy beach sometime. No matter how carefully you work, the walls keep sliding and collapsing inward. Now scale that problem up to a depth of about 1,300 feet. If they tried to break through it with conventional excavators, the project would simply become economically unfeasible, and the soft underground walls, crushed by the immense weight above them, would start squeezing inward with terrifying force. They'd collapse and bury the shaft faster than the engineers could even react. To keep such unstable walls from instantly caving in, you'd have to pour millions of tons of concrete underground and reinforce everything with a massive steel frame. The cost of this would instantly skyrocket. The project would die from runaway expenses before it ever left the drawing board. No sane investor would put a cent into it. So is that the dead end? Without a huge underground void, is the super turbine just a useless chunk of metal? This is where the engineers reveal their trump card. It turns out they don't need to dig through all that terrifying, constantly collapsing Texas sand at all. Nature already did the hard part for them millions of years ago, and in the most perfect way imaginable. Right beneath the flat Gulf Coast lies an underground marvel: salt domes. These are not thin little layers of table salt like the stuff we sprinkle on food. We're talking about colossal, solid formations of rock salt that can rise from miles underground. They stretch downward in enormous masses, deep into the earth. These giants are the remnants of ancient oceans that dried up long ago. And for modern engineers, they're basically a gift. The thing is, rock salt's a unique material, incredibly malleable, pliable, and easy to shape. To create a gigantic cathedral-sized cavern inside it, you don't need jackhammers, tons of explosives, tunnel-boring machines, or an army of workers. Why spend billions on heavy machinery when physics and chemistry can do the dirty work for you? Engineers use an elegant technique called solution mining, where the main tool is ordinary water. The process is almost beautifully simple. From the surface, they drill a narrow, technical well straight into the salt formation. Then they pump water down under high pressure and the water begins dissolving the salt around it. The resulting brine is pumped back to the surface, and inside the salt body what remains is a perfectly smooth, fully sealed cavern of enormous size. It's like a giant empty cup underground, big enough to swallow an American skyscraper. And we're not talking about some abstract speculation from academic papers. In similar man-made salt caverns across Texas and Louisiana, the U.S. government's been storing part of its strategic petroleum reserve for decades. Hundreds of millions of barrels of crude oil. The salt walls can withstand immense underground pressure, naturally seal tiny cracks, and keep liquid trapped inside for years without leaking a single drop. But this time, there won't be oil inside the domes. Specialists at Cavern Energy looked at these ready-made underground reservoirs and came up with something genuinely brilliant. Instead of using them for passive storage, they designed a closed-loop system that could turn these salt caverns into a massive battery. In fact, the engineers didn't invent the idea from scratch. They took an old, proven technology, pumped storage hydropower, or PSH for short, and radically reimagined it. More precisely, they buried it deep underground and added compressed air. In the conventional world, a pump storage plant uses two huge bodies of water at different elevations. One reservoir sits high up on a mountain while the other sits far below at its base. When demand for electricity suddenly rises, water from the upper reservoir is released downward. It rushes through pipes, spins a turbine, and generates power. Then, when the grid has too much electricity and prices drop, powerful pumps send the water back uphill. It basically works like a giant water battery. But we remember the central problem: the Texas coast has no mountains. So the team at Cavern Energy came up with a clever trick. Instead of two open lakes on the surface, they create enormous sealed salt caverns underground. One cavern's positioned closer to the surface, while the second one is much deeper nearby. The difference in elevation between them is enormous, about 1,250 feet. That's essentially a mountain, except it's buried vertically underground. This hidden mechanism is genius in its simplicity. Picture a normal Texas summer evening. It's hot, humid, and miserable. Millions of people come home from work and crank up their air conditioners at the same time. The state's power grid begins to groan under the strain. At that critical moment, operators open the underground valves, and this is where the key innovation kicks in. A giant cushion of compressed air, sitting at around 46 atmospheres, acts like a piston and forces heavy salt brine out of the upper cavern with tremendous power. The high-pressure flow slams into the turbine blades. The metal rotor spins up, generators immediately send huge amounts of electricity into the grid, and the cities avoid a sudden blackout. Meanwhile, the spent brine obediently flows back underground into the lower cavern. Then, once peak demand passes, say late at night when the cities are asleep but Texas wind turbines are still spinning and producing cheap surplus electricity, the system switches into charging mode. At this moment, powerful pumps on the surface come alive. They pull brine from the lower cavern and force it back into the upper reservoir, pushing against the compressed air. The liquid returns to its starting point, and the enormous underground battery is fully ready to work again. At first glance, it sounds like a perfect, clean engineering solution. But this elegant system has one dangerous and merciless natural enemy, and it's circulating right through the power plant's pipes. Meet the main character of this story, concentrated brine, the fluid engineers use instead of ordinary water. Remember how saturated this salt water is? Since it contains so much dissolved salt, the brine becomes extremely dense. In practical terms, this underground liquid is about 20% heavier than fresh water, and that's both the project's biggest advantage and its most serious technological challenge. When a fluid this heavy races through pipes under pressure, it hits the turbine blades much harder than fresh water would. The logic is simple. The flow is denser, the mass is greater, and that means it transfers noticeably more energy to the turbine. As a result, engineers can squeeze more efficiency out of the underground system without having to make the reservoirs absurdly large. From a business standpoint, that's a huge win. But salt is the sworn enemy of metal. If you've ever left anything made of iron near the ocean, you know how quickly it starts to rust. Now imagine concentrated brine constantly circulating through pipes under extreme pressure. If the engineers tried to save money by installing a standard steel turbine, this brutal saltwater environment would destroy it in short order. The metal would corrode, the expensive equipment would turn into useless scrap, and the project worth millions of dollars would be dead. To solve that problem, the developers have to bring in serious material scientists. Right now, they're selecting specialized corrosion-resistant alloys and protective coatings that can withstand this aggressive flow of salt water for decades. And while one group's searching for the perfect material for the pipes and turbines, another group has already answered the obvious question: what do you do with the millions of tons of salt that are washed out of the ground when these gigantic caverns are created? No one's planning to simply dump the flushed-out brine into the ocean or store it for years in giant surface evaporation ponds. Instead, engineers are turning it into a full-fledged commercial product. The thing is, the Texas Gulf Coast is the largest hub of the U.S. chemical industry. And for the massive plants operating there, a clean, ready-to-use salt solution like this is an extremely valuable raw material, the kind they gladly line up to buy. Normally, these facilities have to purchase ordinary solid rock salt. It has to be shipped in by rail, unloaded, and then dissolved in water on site, which takes a huge amount of time, energy, and money. Here, engineers are offering them an endless stream of ready-made liquid concentrate of ideal quality. The plants are happy to take it in enormous volumes directly from the drilling site through a pipeline system. At chemical complexes, this brine is processed through electrolysis to produce pure chlorine and caustic soda. These are essential building blocks used to make plastics, polymers, detergents, paper, and hundreds of other everyday products. The remaining solution can be used to produce high-quality evaporated table salt, as well as industrial de-icing agents that road crews spread on highways during the region's rare freezes. The result is a highly profitable, nearly waste-free cycle. Selling this salt-based feedstock can cover a huge share of the ongoing costs of drilling deep wells and washing out the caverns. The project essentially starts generating real revenue and partly paying for itself while large-scale construction's still underway. And this happens long before the first stream of heavy fluid ever passes through the turbines. But despite all the economic upside, working with salt domes requires surgical precision and strict oversight. History has shown what can happen when people interfere too carelessly with the fragile structure of these underground formations. The most famous example happened in 1980 in neighboring Louisiana, at Lake Peigneur. Two industries were operating side by side. A Texaco oil rig stood on the surface of the lake, while deep beneath the lake bed inside a salt dome, miners were extracting salt. After a simple calculation error, the drillers on the platform missed their target. They accidentally punctured the roof of an active salt mine. Lake water began pouring into a small hole just 14 inches wide. The water immediately started dissolving the soft salt around it. Within hours, that tiny opening turned into a massive void. A massive whirlpool formed on the surface of the lake. The whirlpool swallowed the drilling platform, 11 huge barges, a tugboat, and part of a nearby island, trees and all. The lake literally drained into the earth. Fortunately, the miners and oil workers were evacuated in time and there were no casualties. And this isn't just ancient history. In 2012, another disaster struck in Louisiana near Bayou Corn. There, a company, Texas Brine, had been solution mining a salt cavern for industrial use. Engineers had created the cavern too close to the outer edge of the salt dome. The thin wall simply couldn't withstand the immense pressure from the surrounding rock and collapsed inward. At the surface, the ground began sinking into the water. A sinkhole opened up and eventually grew to the size of several football fields. Eyewitnesses watched as the sinkhole swallowed enormous trees and chunks of land in real time. As natural gas was leaking from underground, authorities had to urgently evacuate an entire nearby residential community. Looking at these historic failures, local people in Texas are asking a perfectly reasonable question. Why take that risk at all? Why build a project that could potentially trigger events like these? The answer lies in one urgent and highly consequential problem. Texas desperately lacks reliable ways to store electricity. Today, the state's the U.S. leader in renewable energy production. Its enormous wind turbines and sprawling solar farms generate vast amounts of power, already accounting for more than 30% of the state's total electricity generation. But engineers have run into a harsh natural reality they simply can't control. The sun shines brightest during the day when many people are at work. Peak electricity demand, however, hits in the evening when millions of Texans come home and switch on their lights, TVs, and powerful air conditioners all at once. By then, the sun's already set, coastal winds can suddenly die down, and the state's power grid's left with a massive, dangerous shortfall. Experts call this problem the duck curve. During the day, so much clean energy is produced that there's almost nowhere to put it. But in the evening, that energy suddenly becomes scarce. To keep the entire state grid from collapsing, the gap has to be filled almost instantly. The most obvious solution is to install lithium-ion batteries, similar to the ones used in smartphones and electric vehicles, but on the scale of a state as large as Texas, that becomes an incredibly expensive and inefficient proposition. Even the most advanced chemical batteries can usually support the grid for only 2 to 4 hours. On top of that, they cost billions of dollars and begin to permanently degrade after roughly 10 years of service. What Texas really needs is a different kind of solution: long-duration energy storage. It needs a powerful industrial system capable of delivering gigawatts of electricity around the clock for days at a time without losing capacity as the years go by. And vast underground salt caverns turn out to be a relatively cheap, reliable, and environmentally friendly way to create that kind of giant battery. Just how badly the state needs such a long-duration reserve became painfully clear only a few years ago during a major natural disaster. In February 2021, the brutal winter storm Uri swept across Texas. It brought record-breaking cold and snowfall to a southern state whose energy infrastructure was completely unprepared for it. As temperatures plunged, massive wind turbines quickly iced over and stopped turning, while critical instruments and pipes at natural gas plants froze solid. The grid couldn't handle the strain and effectively collapsed. More than 4 million people were left for days in freezing homes with no electricity, no heat, and no reliable communication. If the state had been relying only on conventional lithium-ion batteries, they would have been drained within the first few hours of the crisis. Lithium batteries also perform poorly when exposed to extreme cold outdoors. An underground hydroelectric storage system, by contrast, would be largely protected from harsh weather and blizzards. The giant caverns are buried deep underground, where temperatures remain stable at around 68 to 86 degrees Fahrenheit. Even the above-ground equipment's protected by salt. Concentrated brine doesn't freeze inside the pipes until temperatures fall to about -6 degrees Fahrenheit. As a result, the system can keep supplying power for roughly 12 hours straight, helping protect cities from a blackout. The potential of this technology is truly impressive, but how many of these facilities can actually be hidden safely underground? In fact, the scale of the geological potential here is staggering. Studies by American experts suggest that along the Gulf Coast alone, there are currently more than 160 suitable salt domes sitting completely unused. That's an enormous natural resource already shaped by geology and essentially ready for industrial use. If engineers can tap into the potential of these underground cavities, the region could build a single distributed storage network with a total capacity of up to 50 gigawatts. To put that number into perspective, that would be enough clean power to supply roughly 25 million typical American homes during peak demand hours. And the most practical part of this approach is that the largest and bulkiest pieces of power plant infrastructure would be safely hidden deep underground. At ground level, the project takes up the absolute minimum amount of usable space. All that's needed is a small fenced-off area for a technical building, modern pumps, and pipe distribution units. There would be no need to take tens of thousands of acres of valuable land out of use, as often happens when building massive solar farms or installing hundreds of large wind turbines. The familiar coastal landscape would remain almost untouched. It all sounds like a glimpse of the technological future, but where exactly does this massive project in Texas stand today? At the moment, Cavern Energy is in the design phase and is preparing to launch a 1-megawatt pilot facility. To save both time and money on leaching new caverns, the engineers plan to use an existing salt cavern left behind by earlier industrial operations. The main goal of this test is to prove the technology under real-world conditions, test the pumps, and confirm that the turbine's new corrosion-resistant alloys can withstand years of exposure to a harsh, dense brine flow. If the trials are successful, the project will move into the commercial stage. First, the company plans to build a 5-megawatt demonstration plant where the caverns will be created specifically to serve as reservoirs for pumped hydro storage. In the future, the technology could be scaled up like building blocks, linking underground modules into massive energy hubs of up to 125 megawatts each. The project is a strong reminder that solving some of the hardest energy challenges doesn't always require inventing futuristic new technologies. Sometimes it's enough to take the old, proven principle behind a conventional hydroelectric plant and combine it with a region's unique geology. That means that Texas, with its flat landscape, may have a real chance to gain a gigantic, almost invisible battery, one that could operate reliably deep underground inside ancient salt domes.